Hi guys, welcome back to engineeringtalks.com. The previous video was about the shear force and bending moment diagrams of a simply supported beam with a uniformly distributed load. In this video, we'll go through the shear force and bending moment diagrams of a simply supported beam subjected to a uniformly distributed load and multiple point loads like this. So, happy learning, and if you haven't subscribed the channel yet, please do subscribe and press the bell icon. Here I have shown a simply supported beam of length 10 meter over which a uniformly distributed load with rate of loading 10 kilonewton per meter acts over a length of 4 meters along with 2 point loads 50 kilonewton and 40 kilonewton. Now due to this UDL and 2 point loads acting over this beam, we will have reactions at both the supports of the beam. Let RA be the reaction due to hinge support at the end A and let RB be the reaction due to roller support at the end B. Now let's find out these two reactions due to the externally applied UDL and point loads. We know that for solving the numerical problems, we have to convert the UDL into a point load whose value will be equal to the product of the rate of loading and the length of the UDL. Here the rate of loading is 10 kilonewton per meter and the length of the UDL is 4 meters. So the point load will be equal to 10 into 4 kilonewton and it will be acting at the center of the UDL. The UDL is 4 meters in length. So the center of the UDL will be at a distance of 2 meters from both the points C and D. So the point load will be acting like this. We know that the moments at both the supports of a simply supported beam, that is MA equal to MB equal to 0. I have already explained these things in the previous videos, so please watch those videos in order to clarify your doubts. Now, in order to find out these reactions RA and RB, we have to take the moments about A or moments about B. Let's take the moments about A. So, summation MA will be equal to 0, right? Now, let's consider a section at this point A. Now, all these loads and reactions are present on the right portion of the section. So, on the right portion of the section, we have a reaction force RB acting in the upward direction and having a tendency to rotate the beam in the anti-clockwise direction with respect to this section. So, any moment in the anti-clockwise direction on the right portion of the section is considered as positive. So, the moment at this section due to this reaction force RB will be positive and the moment will be equal to RB into perpendicular distance. So, the perpendicular distance is 10. So, it will be RB into 10. Now, this point load 40 has the tendency to rotate the beam in the clockwise direction with respect to this section. So, any moment in the clockwise direction on the right portion of the section will be considered as negative. So, all these point loads, that is 40 kilonewton, this is also 40 kilonewton and this 50 kilonewton, all these point loads will be producing moments in the clockwise direction with respect to this section. So, the moments due to these point loads at this section will be negative. Now, the moment at this section due to this point load will be 40 into perpendicular distance. So, perpendicular distance is 6. So, minus 40 into 6. Now, the moment at this section due to this point load will be 40 into perpendicular distance. Perpendicular distance is 4. So, minus 40 into 4. Now, due to this point load 50 kilonewton, the moment at this section will be minus 50 into 2, which will be equal to 0. Now, we can find out the value of RB from this equation. So, RB will be equal to 40 into 6 plus 40 into 4 plus 50 into 2 by 10. That is 240 plus 160 plus 100 by 10, which is equal to 500 by 10, which is equal to 50 kilonewton. Now, let's consider the equilibrium of the forces. So, summation Fy will be equal to 0. So, Ra minus 50 minus 40 minus 40 plus Rb will be equal to 0. We know the value of Rb now. So, we can substitute that in this equation and get the value of Ra. So, Ra will be equal to, we'll take all these terms to the RHS. So, Ra will be equal to 50 plus 40 plus 40 minus RB. RB is 50. So, minus 50. So, it will be equal to 80 kilonewton. So, Ra equal to 80 kilonewton and Rb equal to 50 kilonewton. Let's find out the shear force values acting along the length of the beam. First, let's consider a section between the points A and C like this at a distance of say x meters from the end A. So this distance is x meters. Now we have to find out the shear force value acting at this section. For that we have to consider either the left portion or the right portion of the section. Let's consider the left portion of the section. So on the left portion of the section we have a reaction force Ra acting in the upward direction. And we know that shear force is equal to the algebraic sum of the forces acting on either the left portion or the right portion of the section. Here, since we have considered the left portion of the section, it will be equal to the algebraic sum of the forces present on the left portion of the section. Here we have only one reaction force. So, the shear force is equal to Ra, and any force present in the upward direction on the left portion of the section is considered as positive. Therefore, the shear force at this section is equal to plus Ra. So, this shear force remains constant between the points A and C, and it will be equal to plus 80 kilonewton. Therefore, at the point A, the shear force is equal to plus 80 kilonewton and it remains constant between the points A and C. In order to find out the variation of shear force between the points C and D, we have to consider a section between these two points. Let this section be at a distance of x meters from the point C. Now we have to convert this much portion of UDL into a point load whose value will be equal to rate of loading into the distance of the UDL. So the rate of loading is 10 kilonewton per meter and the length is x meters. So the point load will be equal to 10x acting in the downward direction. Therefore, the shear force at this section will be equal to Ra minus 50 minus 10x. Ra is 80 kilonewton. So 80 minus 50 minus 10x will be equal to 30 minus 10x. Therefore, the shear force at this section will be equal to 30 minus 10x. Now, when this x becomes equal to 4 meters, this section reaches the point D, right? Now, the shear force becomes equal to 30 minus 10 into 4. That is 30 minus 40, which will be equal to minus 10 kilonewton. So, just before adding this 40 kilonewton, the shear force will be equal to minus 10 kilonewton. Therefore, the shear force varies from a value of 30 kilonewton at the point C to a value of minus 10 kilonewton at the point D just before adding this 40 kilonewton. And we know that the shear force varies according to straight line law for a uniformly distributed load. We saw this in the previous video. Therefore, the shear force just on the LHS, like we can say that just on the LHS of D, that is just before adding this 40 kilonewton, the value of shear force is minus 10 kilonewton. Now at this point D, we have a point load 40 kilonewton as well, and it is acting in the downward direction. So the shear force at the point D will be equal to 80 minus 50 minus 40 minus 40, which will be equal to minus 50. That is minus 10 minus 40, which will be equal to minus 50 kilonewton. Therefore, at the point D, the shear force again decreases from a value of minus 10 kilonewton to minus 50 kilonewton. Now, this value of shear force, that is minus 50 kilonewton, remains constant between the points D and B because we don't have any other point loads between these two points. You can even check it by considering a section between these two points. So, the shear force at this section will be equal to the algebraic sum of the forces present on either the left portion or the right portion of the section. So, you can consider the left portion of the section. So, on the left portion we have plus 80 minus 50 minus 40 minus 40, which is equal to minus 50. You can even consider the right portion. So, on the right portion we have RB in the upward direction. So, RB is 50 kilonewton and a force in the upward direction will be considered as negative on the right portion of the section. So, minus 50. Therefore, the shear force at this section is minus 50 and it remains constant between the points D and B. Let's draw the shear force diagram. For that, we have to draw the baseline first. This is the baseline. Now, at this point A, shear force is equal to plus 80 kilonewton. So we'll mark it above the baseline like this. Now this value remains constant between the points A and C. So between the points A and C, we have the shear force value equal to plus 80 kilonewton. Now at the point C, we have a point load of 50 kilonewton, and due to which this shear force value reduces from plus 80 to plus 30 kilonewton, and we'll mark this decrease using a vertical straight line downwards like this, so that this portion is plus 30 kilonewton. The shear force at the point C is 30 kilonewton. Now between the points C and D, shear force decreases from a value of 30 kilonewton to a value of minus 10 kilonewton, and it varies according to straight line law. So we can mark this variation using a straight line like this, so that it varies from plus 30 kilonewton at the point C to minus 10 kilonewton when it reaches the point D. So this is minus 10 kilonewton. But at the point D, we have a point load of 40 kilonewton, due to which this shear force of minus 10 kilonewton gets further reduced to minus 50 kilonewton. So we can mark this decrease using a vertical straight line downwards like this, so that this much is minus 50 kilonewton. Now this value of minus 50 kilonewton remains constant between the points D and B, and the shear force at B is minus 50 kilonewton. So this is the shear force diagram for this simply supported B. Now you can shade these two regions and mark it as positive and negative. This is positive and this is negative. And here the shear force is equal to 0. So let's mark this point as E. Okay. Here at this point E, shear force is equal to 0, right? Let's find out the location of this point. Let this point be located at a distance of x meters from the point C. Now the shear force at this point will be equal to plus 80 minus 50 minus 10x, right? Because the rate of loading here is 10 kilonewton per meter and the distance of the UDL is x meters. Therefore, the equivalent point load will be equal to 10 into x. Therefore, the shear force at E will be equal to 80 minus 50 minus 10x, which will be equal to 0, because the shear force at E is equal to 0. Now 10x will be equal to 30 and x will be equal to 30 by 10, which will be equal to 3 meters. Therefore, the point E, that is the point of 0 shear force, is located at a distance of 3 meters from the point C. Let's now find out the bending moment values along the length of the beam. We know that MA equal to MB equal to 0. Now we have to find out the bending moments at C and D. So let's first find out the bending moment at the point C. For that, let's consider a section at the point C. Now this is the left portion of the section. Here we have a reaction force RA, which is equal to 80 kilonewton, acting in the upward direction and producing a clockwise direction with respect to this section. Therefore, the moment at this section due to this RA will be positive and it will be equal to 80 into perpendicular distance. Perpendicular distance is 2 meters. So, the moment at this section will be equal to 80 into 2, which is equal to 160 kilonewton meter. Therefore, MC is equal to 160 kilonewton meter. Now we have to find out the bending moment at the point D. So let's consider a section at the point D. Now this is the left portion of the section, and RA has the tendency to rotate the beam in the clockwise direction with respect to this section. So the moment at this section due to RA will be positive. Now these two loads have tendency to rotate this beam in the anti-clockwise direction with respect to this section, and any moment in the anti-clockwise direction on the left portion of the section will be considered as negative. Therefore, moments created due to these two loads at this section will be negative. Therefore, the resultant moment at this section will be equal to RA into 6, RA into 6 minus 50 into 4 minus 40 into 2, which will be equal to 80 into 6 minus 200 minus 80, which is equal to 480 minus 200 minus 80, which is equal to 200 kilonewton meter. Therefore, the moment at the point D, MD will be equal to 200 kilonewton meter. From the shear force diagram, it is clear that shear force is 0 at the point E. So let's find out the bending moment at this point. This point E is located at a distance of 3 meters from the point C and 5 meters from the point A. Now for finding out the bending moment at this point, we have to convert this UDL into an equivalent point load whose value will be equal to 10 into 3, that is 30 kilonewton, and it will be acting at a distance of 3 by 2 from this section. So the bending moment at this section will be equal to RA into 5 minus 50 into 3 minus 30 into 3 by 2. 3 by 2 is 1.5. So 80 into 5 minus 50 into 3 minus 10 into 3, that is 30 into 1.5, which will be equal to 400 minus 150 minus 45, which will be equal to 205 kilonewton meter. So from this we can understand that the bending moment is maximum at this point E where the shear force is 0. Let's draw the bending moment diagram. For that we have to draw the baseline first. Now at this point A, bending moment is equal to 0. Now at this point C, we have bending moment equal to 160 kilonewton meter, and the bending moment between the points A and C varies according to straight line law. So let's mark this variation using a straight line like this. Now between the points C and D, we have UDL. So for a UDL, the bending moment varies according to parabolic law. So if you have any doubt in this, please watch the previous video. Now we can mark this variation using a parabolic law. But in between the points C and D, we have the point E where the shear force is 0. And at this point, bending moment is maximum. So first let's mark the bending moment between the points C and E. And it varies according to parabolic law. Now between E and D, the bending moment decreases from 205 to 200 kilonewton meter. Now from this point, that is from the point D to the point B, bending moment varies according to straight line law. So we can mark it using a straight line like this. And you can shade this region and mark it as positive. So this is the bending moment diagram for a simply supported beam with a UDL like this and 2 point loads. These are the shear force and bending moment diagrams for a simply supported beam subjected to a uniformly distributed load along with 2 point loads like this. And here we have the point E where the shear force is 0 and the bending moment is maximum at the point where the shear force becomes 0 after it changes its sign from positive to negative or vice versa. And the maximum bending moment is given by 205 kilonewton meter. Please do like and share the video and subscribe the channel. Thank you.